seminar that I'm giving today. And I am Sai, and I work with Joram Bressler, and I did my master's and PhD here, and I finished my PhD just in December. And I'm now a lecturer at ECE. I teach 310 and 311. And I'm postdocing just for a while with Joram. So that's about me. And today's topic is going to be adaptive sparse representations of signals and images and applications of these adaptive sparse representations. Okay. So before I go into the main subject of the talk, which is the adaptive part, I want to just briefly give an overview of what I mean by sparse representations. So I'm going to talk about a bunch of different linear sparse signal models, just to introduce everyone to the topic. So there are a couple of pretty well-known sparse signal models, and the word sparse just means that you're looking at a signal that is mostly zero. So that's where sparsity comes from. So a very well-known and kind of famous model for sparsity is the synthesis model, which says that if given a signal y and some dictionary d, a dictionary is just a matrix, and the columns of the matrix constitute what are known as atoms. So given a signal y and a dictionary d, the model says that y can be represented as a linear combination of a few set of columns of the dictionary d. So y can be written as d times this sparse vector x. The vector x is mostly 0. And that's this synthesis model. More generally, you can say that y can be modeled as d times x plus some perturbation e. This corresponds to a more realistic scenario. And the assumption would be that E is small, so that the model works for any given signal. And now, so given a signal y in the dictionary D, how do you find a sparse representation or a sparse code in this dictionary for that signal? You end up solving this problem shown over here, which is known as the synthesis sparse coding problem, which is for people in signal processing, this is a very familiar problem. You essentially minimize the residual or the modeling error in the signal domain, which is y minus dx, 2 normal square of that, subject to sparsity constraints on x. And okay, so the 0 norm basically counts the number of non-zeros in x, for those who are not familiar. And this problem is unfortunately NP hard, or non-deterministic polynomial time hard. So it is a pretty hard problem. And although it's an NP hard problem, there have been several algorithms that have been proposed over several years for solving this kind of problem. And they can be either greedy algorithms or relaxation algorithms. And although these algorithms have been shown to solve this problem under certain assumptions, they tend to be computationally expensive for large-scale settings. And I'll be pretty much repeating the key phrase large-scale settings throughout this talk, because that's what the focus is going to be. And another popular model, or the complement of the synthesis model, is the analysis model, which says that given a signal y and an analysis operator or dictionary omega, it is basically typically a tall matrix. You have that omega times y is sparse. And so as opposed to the synthesis model where you try to synthesize the signal using a sparse set of combinations of the atoms or columns of the dictionary, here you essentially apply the rows of omega on the vector y, or the signal y, to create something that's sparse. So a way to understand, for example, this model is that the signal lies in a union of subspaces. So each subspace is formed by a set of a small set of columns of the dictionary. And you can have different kinds of sparsity patterns. Here, there is the locations of the non-zero, so that's why the signal lies in a union of subspaces. On the other hand, here, because you're finding sparsifiers for the signal can be thought of as living in a union of null spaces. Okay. And more generally, this model has been extended to what is known as the noisy signal analysis model, which says that your signal Y is a signal Q plus some small perturbation E, and omega times Q is sparse rather than omega times Y. So this is a generalization. And there has been something called the analysis sparse coding problem that has been proposed, which in this NSAM model tries to find the sparse code by minimizing the residual Y minus Q squared, and the sparsity constraint is on omega Q. Right? And again, this problem has been shown to be NP hard, and there are, again, approximate algorithms that have been proposed for solving this problem. And again, they tend to be computationally expensive for large-scale settings.
What is the co-sparsity now? T, co-sparsity?
Yes, that's T.
What is that? What is that?
Co-sparsity, okay. When you say sparsity, you're referring to the number of non-zeros. When you say co-sparsity, you're referring to the number of zeros. So you want at least T zeros in omega Q, which corresponds to having a
M minus 2 at
yes.
M minus 2.
Okay, and in our group, we have been working on another extension of the analysis model, or another generalization, an alternative generalization, which says that given a signal Y and an operator, or what we call a sparsifying transform, W, we have W times Y is approximately sparse. So you have WY is some sparse vector X plus some small perturbation eta. So unlike the noisy signal analysis model, where the perturbation E is in the signal domain, the perturbation here is in the transform domain, or the analysis operator domain. So although this seems like a minor difference, it leads to several key advantages in various settings. So for example, if you want to find the sparse code in the transform model, all you need to do is you need to minimize the transform domain residual WY minus X. You are given W and Y here, subject to the sparsity constraint on X. And this problem is very, very simple, because this is just projecting WY onto the L0 ball, or S L0 ball, because you're using the sparse code S, and you obtain the solution by just thresholding WY and keeping the S largest magnitude elements. So it's a pretty simple sparse coding solution. And this kind of a model is not unusual, because people have been, or this model is satisfied by transforms such as DCT, the discrete cosine transform, or the wavelet transform for images or image patches. So you apply these transforms to images or other kinds of signals, you get something that's approximately sparse, and people have
but
used
all
it.
those are orthogonal transforms. They are, the matrix is squared, that is, M is equal to N.
Yes. By using over-completeness, you get a richer model. And why? Because you're allowing, so by allowing more rows in this W, you can capture more of these null spaces. Because different signals may lie in different sort of null spaces. And because you're looking at a union of null spaces, to allow for a richer model, having more of these rows allows for greater collections of these null spaces. Just like in the synthesis case, by having a fatter or a longer dictionary, you're allowing for more subspaces in the union of subspaces. Okay, so all this was about just the models, and the focus of this talk is on the adaptive part. So you want to kind of learn the models from the data, or this is kind of usually referred to as data-driven adaptation. And this has become kind of very popular in recent years. People have been doing it in lots of different applications. So if you want to learn synthesis or analysis dictionaries, it turns out that these problems, these learning problem formulations, tend to be typically non-convex and NP-hard. And there have been several algorithms. This is just a very small list. It's not an exhaustive list. There have been several algorithms that have been proposed for example, for synthesis dictionary learning, such as MOD. KSVD is very, very well known. And these are all algorithms for synthesis dictionary learning, and similar algorithms have been proposed for learning analysis dictionaries or dictionaries that satisfy the noisy signal analysis model. And these are just some of these methods. And a common property of many of these methods is that they tend to be computationally expensive because of the NP-hard sparse coding that's involved in the learning. And most of these algorithms may not even converge. So we are going to talk about sparsifying transform learning, which kind of, it turns out it helps alleviate some of these drawbacks of the other models that I just talked about. And recall that sparsifying transform is just an operator. It can be a square matrix or it can be a tall matrix. You're learning an operator that sparsifies your signals from some set of training data. That's the goal over here. And there are various flavors of transform learning that we have been working on and we have proposed over several years. And this is just a listing of several of these kinds of transform learning methods. Some of these methods learn square transforms, that is, they learn square matrices. And there are others that learn overcomplete or kind of tall matrices. And there have been several applications that we have explored, just plain sparse representation of signals or images, or image denoising or video denoising, classification, compressed sensing, a bunch of different applications, and depending on whether time permits, I'll talk about some of these. Okay, so I want to begin with the simplest form of transform learning formulation that we have proposed in the recent past. And that's about just learning a square transform, a square matrix. So this is the kind of problem that we propose for learning a square transform. And what are we given, first of all? We are given a bunch of training signals. The matrix Y over here is just a concatenation of numerous training signals and training signals in this case. And you want to learn a transform W that sparsifies or approximately sparsifies this training data Y. And X here denotes the matrix of sparse codes. So the columns of X denote the sparse codes or the transform sparse codes of the columns of Y. So the first term in this kind of formulation or objective function models the transform domain residual, or is the modeling error in the transform model. And you want to minimize that in order to learn a good transform. And you also need a regularizer, because if you did not have this regularizer, the solution turns out to be pretty trivial, because W being 0 and X being 0 is a trivial sparsifier for any set of signals. So you don't want to learn trivial or meaningless solutions. So in order to enforce some measure of information in the transform, we use a regularizer. And the log determinant essentially restricts solutions to full rank transforms, and it avoids degeneracy such as repeated rows in the transform. And the Frobenius norm term here essentially is to keep the objective function here lower bounded. Otherwise, it can go down to negative infinity in some cases.
So, okay, there are many other regularizers that would have the exact same property. So what's the advantage of that one?
Next slide.
Okay.
Certainly, you can have lots of different regularizers, and depending on what properties you're looking for in your transform, you can have a variety of regularizers. For example, if you want a sparse transform, if the goal is that you want something that sparsifies your data and is also efficient in terms of storage, then you can learn a sparse transform. And here, I call this kind of unstructured transform because I'm not going to enforce additional structures on the transform such as sparsity and so on. But if we just use this regularizer, what are the properties of this transform learning problem? So number one, if there exists a pair W hat X hat such that the model here is satisfied exactly, that is W hat Y is exactly equal to X hat, and W hat is unit conditioned, that is the condition number is 1, and X hat is sparse, that is X hat satisfies the sparsity constraints, then this pair is actually a global minimized minimizer of this problem, or usually this is referred, we say that such a pair is globally identifiable by solving this problem. So when you have a kind of noiseless model for the data, you can use this, and noiseless in the sense there is no deviation in the transform domain, and the transform itself is unit condition, then you can find this transform exactly by minimizing this problem. So this problem essentially tends to favor transforms that provide low sparsification, which is good, and also good conditioning. And it turns out that good condition numbers lead to better performance in applications like denoising. So that's why the condition number it's good to control the condition number using this regularization. And actually minimizing this regularization encourages reduction of the condition number, and as the parameter lambda, or the weight lambda tends to infinity, you can actually get a complete control. You can actually, this condition number of these minimizers will span the entire range of conditioning.
Can you say a bit more about what that means? It encourages reduction of the condition number? Is it a monotonically non-decreasing function of the condition number?
Yes, so the regularizer can be upper, so the condition number can be upper bounded by a monotonically increasing function of the regularizer.
So the cost function is convex in W, right, for fixed x. So
it is not convex in W because the log determinant without
it's concave. That's concave.
We are not restricting it to be positive semi-definite.
Oh, okay.
Because you could do that. You could try restricting W to be just positive definite, but that turns out to not lead to very interesting transforms, really, because a lot of transforms that we know, like the DCT or the wavelets, these transforms are not positive definite.
Sure.
So that turns out to be pretty restrictive to enforce a positive definite constraint. Okay, so so this regularizer helps control the condition number.
Sorry, if you had instead of if you had say 1/2 log determinant of W times W transpose, would that make any sense? Would that be easier in some way? Would that
in the case of a square transform,
it's the same.
It's the same.
But for non-square transform,
yes,
not
that's
the same.
in another paper. So.
But is that a good idea to use?
It is. It kind of. I thought I could put that in this talk, but already this talk is too long. So, but there is a paper that we have. I can show you which one. This one in ICAS 2013, where we kind of learn a tall transform with this constraint on the log determinant of W transpose W, and and we also, it's not just it is not enough to just constrain that, because even if you constrain the log determinant of W transpose W, you can still have repeated rows in a tall matrix. So you need to constrain the coherence of the transform. So what we showed is that using that kind of a formulation, you can learn interesting types of transforms like Grassmannian frames or unit norm type frames. So it encourages certain kinds of properties. Okay, back to square transforms. Okay, so as the parameter lambda goes to infinity, the minimizer here, the condition number of the minimizer tends to 1. So that's what I wanted to say. So how do you solve this kind of a transform learning problem that I just showed on the last slide? For the in prior work for synthesis or analysis dictionary learning, people have proposed a lot of alternating type algorithms, alternating minimization algorithms. So in this case, we also propose alternating minimization algorithms, but unlike in the synthesis or analysis or noisy analysis dictionary learning cases where you encounter an NP-hard sparse coding problem, here things turn out to be much simpler. So if you were to solve P1 by alternating between updating sparse coding step, where you minimize over the sparse code matrix X, you kind of solve this problem, and you get a very cheap solution that involves just thresholding the columns of WY and retaining only the S largest magnitude elements in each column. And also now you also have one more step, which is called the transform update step, where you minimize the cost function over the transform W with a fixed sparse code, and that is this unconstrained minimization problem that has this log determinant and a bunch of squared Frobenius norm penalties. And previously, we had proposed an iterative method based on nonlinear conjugate gradients for solving this problem. More recently, we have derived a closed form solution for this kind of a problem that is shown over here. In order to compute the solution in closed form, you need to compute a bunch of square roots or singular value decompositions. For example, you need to compute the square root of this matrix, y transpose plus this scale identity, and that is what is this L matrix, it's a square root. And you need to compute a singular value decomposition of L inverse times y x transpose. Y is the data, x is the Sparse code matrix. And once you compute these quantities, you can compute the solution for this problem in closed form.
So that's on paper, but in reality, for large-scale problems, you cannot compute that, right?
Yes, later on I'll be talking about online transform learning.
What is L for L?
L is a square root.
Square root.
Square root of matrix. And you can have different kinds of square root for a matrix, but the solution is invariant to the specific choice of the square root. And the solution is unique if and only if the matrix yx transpose is non-singular. Okay. So we have this kind of simple alternating minimization algorithm for learning a square transform, where given some training data and some initialization for the transform in Sparse code and given the parameters for the problem, you can alternate between a transform date step and a Sparse coding step until convergence, and you get an output which is the learned transform for the data. So what are the convergence properties of this kind of an alternating minimization algorithm? People have, there have been a lot of papers in recent years talking about alternating minimization of non-convex problems. So this is of particular interest, and you can derive very nice convergence guarantees for the alternating algorithm that we just talked about. In order to do that, we need just one notation. Instead of the constraints that I had in the problem, I will be using the replacement, which is the barrier function, psi of x. Psi of x is plus infinity when the constraint is violated, and it's 0 otherwise. So the problem P1 that I talked about is equivalent to minimizing this unconstrained minimization problem. It has all the terms in the previous cost function plus the barrier function psi of x. Okay, so what can we say about the sequence of iterates generated by this alternating minimization algorithm? Number one, it's fairly trivial to say that the g of wkxk, this is the sequence of objective function values, where wkxk are the iterates in this alternating minimization algorithm. So the sequence of objective function values converges monotonically to some finite value. This is very trivial. And what happens to the iterates, wkxk? You can say that this iterate sequence is bounded, and every accumulation point wx of this sequence is a fixed point of the algorithm, and it satisfies the following local optimality condition. So if you take the accumulation point, any accumulation point wx, and you perturb it in a local neighborhood denoted by this dw and delta x, your objective function will only increase. So it's every accumulation point is a local minimizer of the cost function. And all these accumulation points achieve the same value of the objective, g star, which is the value to which the objective sequence converges. And for simplicity, I'm just saying that you can have only local perturbations, but in our expanded paper, we have shown that some of these perturbations can in fact be pretty large in certain scenarios. So the region where this optimality condition holds need not be too small. Okay, so how do I want to summarize what I just said. So for each initialization of this alternating minimization algorithm, what we have is that the objective function converges to a local optimum, and the iterates converge to an equivalence class of local minimizers. The equivalence relationship is defined in terms of their objective functions being identical. So you can have something like here, this is a hypothetical objective function, and you have an iterate sequence, numbered iterate sequence here, that has two subsequences that converge to two equivalent accumulation points. And these accumulation points are local minimizers of this hypothetical objective. So you need not converge to a unique accumulation point, but all your accumulation points will be equally good, at least in terms of the objective that you minimize. And you can also say that you can also give a kind of global convergence property, and this does not mean that you're converging to the global minimizer, but people have been using this terminology, and it means that you are looking at convergence from any initialization of the algorithm. So the algorithm is globally convergent, that is, it converges from any initialization to the set of local minimizers of this non-convex injector.
Does this mean, actually, I think I missed something, does this mean that all local minima of the objective function are in an equivalence class, or just the ones to which the ones that are accumulation points of the algorithm?
Yeah, the accumulation points of the algorithm belong to an equivalence class.
So that there may be other local optima, but the algorithm just skips over those.
It would depend on the initialization, because this is a local convergence property, so you may go to different local sets of local optima.
Well, so what you've shown here is that there are only two local optima in the optimization criterion, and that obviously then a local a gradient descent would converge to one of those two.
Mm-hmm.
But if one of them is lower than the other, then they're no longer in the equivalence class.
No, but for the iterates here, all the accumulation points will satisfy the exact same objective value.
Right, but they could be a better equivalence class.
There
right?
could be.
Yeah.
This theorem does not, this result does not negate that.
So
it does not
there
prove.
could be local optima that are actually better than the ones to which this algorithm will converge.
That can always happen with local optima.
Yeah.
So the claim is convergence to local optima rather than global optima.
So the claim is convergence to a local optimum, but with this funny extra constraint that all of the local optima to which the algorithm, from any given initialization point.
Yes, it's not a constraint.
Okay, I see.
So you do not require any extra conditions for this result.
Okay.
So no matter what data point, what training data you've given, this result kind of always holds.
Okay, so in this case, if it started on the peak between those two local optima, it could go either way. But if one of them was lower than the other, it would go to the lower one. It would go to something that's in a particular set.
Okay.
Sorry, if I'm understanding you correctly.
It would converge to one of those values in terms of, so the iterates themselves may not converge, they could converge to an equivalence class in a sense, but the objective function converges to a value.
Yeah.
So it converges to a local optimum value.
So what does corollary 2 say? I'm confused by what you're saying.
Oh, this is, so this is just giving the convergence from any initialization. So if you fix the initialization, the algorithm converges to an equivalence class of local minimizers, whereas if you
When you
consider
say equivalence class, you just mean the set of all local minimizers.
no, equivalence class meaning local minimizers that achieve a certain fixed value of the objective. And the value depends on the initialization. But if you want to look at convergence irrespective of initialization, then you can say that the algorithm converges to the set of local minimizers.
So what makes
So it just converges to a local
To
optima.
a local.
yeah, what makes these alternating minimization problems difficult to analyze often is that the cost function is non-smooth in one variable, but here it's smooth in both variables. So
It is not.
It is not.
It is not. See, the
Can you
cost
see the cost
function.
function again?
The cost function here has a barrier function, which is.
Oh, yes, the barrier function. So how do you prove then this property?
You can still prove it.
No, I'm sure you can, but how do you do it?
Let's see. You kind of go through a bunch of steps. So you show that you have to first show that the iterate sequence is bounded, and then you have to show that the accumulation points of the iterates, all of them achieve the same value. And then you can look at the objective function and use some properties of the log determinant and properties of the F0 norm to kind of prove that prove this relationship for any accumulation point.
Oh, because you're essentially doing, you're essentially optimizing a smooth constraint within subspaces where you have this union of subspaces, right?
It is not.
Psi function restricts you. Psi function is infinite if you're off the subspace. So its function is essentially to
But it's,
constrain it that way, right?
see, the number one, the log determinant is not smooth.
Yeah.
It has
okay.
these
Does that
discontinuities.
is not smooth too. Yeah.
And this is not smooth.
Okay.
So
Okay.
Okay, why is the log determinant non-smooth?
So the log determinant is
Because
non-smooth on
on non-singular
On
matrices.
non-
On
okay.
singular matrices, sorry,
Yeah.
on the set of singular matrices. And this is a kind of
But it's
not
still
a
sort
small
of,
set. It's
it's still sort of.
But you get the
almost
log
smooth, right? I mean,
singularity.
the places where those singularities occur are subspaces. So it's sort of, you have constraint to a union of subspaces of a criterion which is smooth except on a union of subspaces. Right?
So I'm not sure about whether the log determinant can be, the barriers in the log determinant can be thought of as dividing the
Because
space
the
of
log
matrices.
function is smooth, right? So that should not be a concern, even though it goes to infinity.
Mhm.
So the big difficulty seems to be with the norm, the L0 norm of x, right? Through the barrier function.
Yes. Okay, let me go forward. Okay, so we have this nice alternating minimization algorithm, and we wanted to do this transform learning because the other alternatives like dictionary learning suffered from a high computational cost. So do we have what we want? We do. So if you look at the cost, computational cost of the proposed alternating minimization algorithm, it scales as a square of the size of the signal. N here is the number of training signals, but n square is the square of the size of the signals, of the training signals. And on the other hand, if you look at popular synthesis or analysis dictionary learning algorithms such as KSVD, the cost mostly scales as a cube of the size of the signal. So there is a big difference in the computational cost, particularly when you're looking at large dimensional signals. And if you look at images, what does this translate to? Because in images, you usually learn the models for patches rather than the entire image. If you learn for a patch, for a square root and by square root and patch, the advantage is there is a scaling in the order by factor n, which is the number of pixels in the patch. Okay, so I had the kind of local guarantee, which was the theoretical result, and we wanted to explore what is the practical behavior of this transform learning algorithm. For example, when you want to learn transforms for images like this one, like this is a well-known image, Barbara. And if you want to learn a transform from 8 by 8 patches of this image at certain sparse level, for example, some level which is 11, how does the algorithm behave? Okay, so here we kind of plot the objective function, the condition number of the transform, the sparsification error, which is the first term in our cost function, for various initializations like the DCT, KLT, which is the Bahunian lobe transform, identity, random Gaussian initialization. So what we observe, at least for images, is that the algorithm is pretty insensitive to initialization. So the objective and all these other metrics converge to pretty similar values from all these different initializations. So, and why is this useful? Because if you look...
Let me understand. So there's a structural constraint on W here that you have this 8 by 8 patch constraint, and so the transform...
the transform is 64 by 64.
Right, right. Or 64 by 64. Huh?
Yes.
So you're constrained to using the same transform
for all the patches.
For all the patches.
Yes.
Okay.
There are other techniques. I mean, there are other variations where you can learn different transforms for different sets of patches. That's something I'll talk about next.
Mm-hmm.
But in this simplest kind of formulation, we learn a single transform for all your signals, for all your training signals. Okay. So how does the learn transform look? For Barbara, the rows of the transform, when they're arranged as patches, they look something like this, and this is how the 2D DCT looks. Okay. So for Barbara, the learn transform does have some similarities with the DCT, although this is not always the case. It depends on the image how the transform looks. But you can see actually the novel features of the learn transform in some of these items. For example, here you can see some of these diagonal textures that are being captured by the learn transform, whereas the DCT does not capture these image-specific variations. Right here. Okay. So how do you measure the quality of the transform that you just learned? Number one, you can look at how well it sparsifies the data that you trained on. So to quantify that, you compute what's known as the normalized sparsification error. which is the sparsification error normalized by the total energy in the transform domain. And if you look at the normalized sparsification error for the DCP, it's about 6.8% for the patches of the image, whereas for the learned transform, it's much reduced, which is about 4.4%. You can also look at something called the recovery PSNR, where you recover the estimates of the patches of the image from these sparse codes that you learned by applying a W inverse, which is this kind of a simple least squares reconstruction in the transform model. And you can compute the peak signal to noise ratio of this reconstruction. And the learned transform gives about 1.7 dB improvement in this case, in this example, in reconstruction over the DCP. So it tends to give better image representations than some fixed Sparse-Affine transforms. Okay, here's another application, very popular application, which is image denoising. Okay, so the goal in denoising is to estimate an image X from its noisy measurement, which is denoted here as Y. So Y is X plus some noise term or perturbation H. And how do we estimate X in this case? We actually work with the patches of X. We have an operator Rj, which extracts the patches, and Rjy here denote the patches of the noisy image. And Xj denote the denoised versions of those patches. And tau is some weight. This is what's usually referred to as a data fidelity term. Signal processing people will know this very well. So you have a data fidelity term that is a function of the patches of the image. So why is this useful? So when all the overlapping patches of the image, so overlapping patches are patches that are kind of on top of each other, not completely but partially. So when you use all the overlapping patches of the image and you enforce the hard constraint Rjx equals Xj for Rj here, then this data fidelity term is just a scale log likelihood for this denoising problem under ID Gaussian noise. But in this case, we are not going to enforce the hard constraint Rjx equal Xj in this problem. And we are going to just focus on denoising the patches. It leads to some computational advantages, so that's why we are doing that. So you have a data fidelity term, and you also need a regularizer to kind of debias your denoise signal from the noisy signal. And people working on denoising will know of lots of different regularizers that people have proposed. And this is just a regularized inverse problem. So once you find the denoise patches Xj, how do you obtain the image X? You obtain the image X as a solution in the system of linear equations here with fixed Xj. So X is obtained by averaging the denoise patches Xj at their the locations in the 2D image, averaging together these overlapping patches.
Sorry, how does this connect with what? So what is Rj what you're using instead of W?
Rj is just an operator that extracts the patch.
So how does this connect with your previous?
That's on the next slide. So this is just a general, just an introduction to a regularized inverse problem. So now we are going to apply transform learning to image denoising. How do we do that? We replace the unknown kind of regularizer in our previous slide, the U function, by the transform learning cost function. So when you do that, you get this more complicated kind of denoising problem. You have the sparsification term, the regularizer on the transform, and the constraint on the sparse codes coming in once you add the transform learning regularizer. And although this problem is quite complicated, you can solve this by alternating minimization, and you can solve this quite efficiently. And notice that we have these sparse key levels here for the patches, Sj, for the sparse codes of the patches. And these sparse key levels are typically unknown, and we have some scheme for adaptively estimating these sparse key levels in our algorithm. So I won't go into that. So this is kind of the overall framework. So if you use this kind of an image denoising approach, how does it work? So you have a noisy image here of the very well-known cameraman image, a noisy version of the well-known cameraman image. And here is a denoised version, number 1.3. And this is a result that's obtained with an overcomplete dictionary, 64 by 256 overcomplete dictionary. So compared to the overcomplete dictionary, the transform method gives somewhat better denoising performance, but it is also much faster. It's about 17 times faster in denoising, for example, this image.
The KSVD is no longer state of the art, right?
It is not, but just for I will be comparing to the state of the art later. But for this example, to just compare the models, I'm using a dictionary learning algorithm, and I use KSVD. Okay, so this completes the first part of my talk on the very simple square transform learning. What's the time?
It's 4:45.
Oh God. Okay. I have like 65 slides, and I already reduced it quite a bit because for my defense I had like 95 slides. So.
So to have you back again later this semester.
Okay, so I basically talked about square transform learning method, and the algorithm that I proposed has some very interesting properties, theoretical and empirical properties, and it seems to work well for representing images or for denoising images. So, okay, so I'm now going to move on to something called a union of transforms, or we call this kind of a transform octopus. It's a long story why I named it octopus, but in the end it just turned out to be a nice catchy phrase. Okay, so typically natural images have a lot of diversity in their content. So for example, in this image you have a bunch of different textures. In this image you also have a bunch of different textures. Like here you have a texture sliding this way, a texture sliding this way over here. Here you have another kind of texture, and here a different kind of texture. So lots of different textures, and it seems to be of interest to learn not a single transform to sparsify these very diverse structures, but to learn a bunch of different transforms. And so we
Sorry, before we continue, I have a question about part one. So isn't it a bit cheating what you did, in the sense that when you apply it to denoising, you train on the clean image itself?
No, on the noisy image.
On the noisy image, okay,
Yes.
okay.
So we are solving so we have the transform learning function as a regularizer
Right.
in the image
Okay.
problem. So you're
That's
learning
right.
and
That's right.
denoising simultaneously.
Okay.
Okay. So we want to learn in many situations a union of transforms. Why is a union of transforms useful? You could do classification, for example. And you could even do denoising better by learning kind of a collection of transforms than just one transform for a very diverse or large image. So what is the kind of problem that we're going to look at? That's the one over here. It's problem P3. So it kind of looks very complicated, but it's actually very similar to the problem that I just discussed in my part one. So you have a kind of sparsification error term and a regularizer involving the log determinants and so on. But instead of having a single sparsification term for all the signals, you have the cost function essentially divided into the components for different classes. So CK here contains the indices of the signals for the kth class. So you want to the goal is to kind of automatically cluster the signals into different classes and learn transforms for the signals in those classes all simultaneously, okay? And so your sparsification error here, you sum over all I belonging to a particular class CK, and then you sum over all the classes. Here we have about K classes, so usually capital K. And then you have a regularizer which also splits up into regularizers for the different transforms. Okay, and the constraint here involves a sparse code constraint, which constrains the sparsity of the sparse codes, and you also have the kind of constraint that the classes, the classes belong, the set of the set of CKs belong to this kind of set G, which is a set of all partitions of 1 is to n, where n is the number of training signals into k disjoint subsets. Okay. So this problem essentially jointly learns a collection of transforms or union of transforms and clusters the data y all simultaneously. And you have these kind of weights here, lambda k, and we actually set the lambda k to be some constant lambda naught times the energy of the signals in the kth cluster. And we do this because it achieves a certain scale invariance of the signals in this problem. So essentially, if you scale the y's by some constant, and if you choose the weights lambda k in this way, the solution is kind of invariant to trivial scalings of the data. And again, there is a similar property like for the square transform learning case. If you let your lambda k's go to infinity, then you end up learning the union of orthonormal or well-conditioned or unit conditioned transforms in the limit. Okay, and I won't go into great details on how you solve this problem. We have proposed a very efficient alternating type algorithm for solving this union of transforms learning problem, and that algorithm again has some global convergence properties. Global convergence as in convergence from any initialization. So I want to show some results. So if you have an image like this, then you really do have a lot of different structures in the image. So if you could learn an octopus or a union of transforms and try to classify the texture, the pixels in the image into different classes. How do you do that? First of all, you take the overlapping patches of the image and you train your octopus or union of transforms on these overlapping set of patches, and this automatically clusters the patches into different groups, and then each pixel is classified into a particular class by taking majority vote from the patches that overlap this pixel. So for example, if you have this kind of an image, and if you run k-means on the patches, you get a classification result that looks like this. So the class 1 is the one in green, class 2 is the one that shows the image pixels. And whereas if you do octopus, you get a much cleaner classification because it's able to adapt or adaptively learn these clusters and the transforms. And compared to the k-means model, the octopus model is richer because it learns really a big transform, not just a single mean vector for a bunch of signals. And this is another example, again, k-means and octopus. You have some interesting results when you do transform learning.
How do you initialize clusters?
We kind of initialize with the k-means result. Okay, so you could also do image denoising using octopus. So the same problem as the one I discussed before, but you use the octopus transform learning as a regularizer in the inverse problem, and you learn the octopus and denoise simultaneously. And then you can obtain some results, and you can compare the results to some other well-known algorithms, such as the GMM Gaussian mixture model denoising algorithm, KSVD BM3D, which is one of the state-of-the-art. And octopus denoises much better, about 0.4 dB better than KSVD, and is faster. And octopus is about 0.4 dB again better than GMM. And the performance is comparable, at least in the low noise levels, to BM3D. And BM3D is not really a dictionary learning algorithm. It does it kind of takes patches and finds similarities between the patches and then groups them together and applies some Wiener filter and DCT and so on, a bunch of different things, heuristics. So, but the performance is comparable in certain cases to BM3D, and I may not be able to get to this in this talk, but when the dimensionality of the problem increases here, the images are not very large images, they are 512 by 512 images. But when we went to videos, for example, and we have results later, but you can ask me to send you the paper if you want. The adaptive transform-based methods actually tend to perform much better than the variations of BM3D for video denoising on these large-scale problems.
So how do you explain that BM3D works better at low SNR?
Oh no, it works better at high SNR. Yes, it works better at low SNR, sorry. Right. Because, see, in Octopus, we are learning the model from the noisy data. And as the noise becomes worse and worse, it kind of limits how well Octopus can perform because you're learning on the noisy data.
What is BM3D? Does it have any special noise criteria?
BM3D, let's see. It doesn't learn anything on the noisy data, so it uses a bunch of fixed operations. it uses the non-local means kind of property. I don't know. But I can tell you this though, that GMM, for example, the GMM method here also, they don't, the GMM method also involves learning these Gaussian mixture models, the covariance matrices and so on for the GMM model. And they learn it on a kind of separate training set, the ones that we compare to. They learn it on a separate training set. And at higher noise, sometimes they perform better, like sigma 100, sometimes they perform better than Octopus. And that's, and sometimes not so much. And that may be because they are learning on the kind of clean data. So BM3 at high noise, I need to think about it. So nice question.
Have you ever tried supervised learning?
No, this is all unsupervised.
So have you tried supervised learning?
No, not supervised in this framework, no.
Yeah.
We haven't tried yet.
Okay.
What is the computational time for this method?
Computational time, it's usually less than a minute to maybe a few minutes, depending on the size of the image.
How about BM3D for the same problem?
So the implement, we were using a MATLAB implementation. BM3D, they have implementations in C, so they tend to be usually slightly faster than what we have right now, but it may change once we go to C. Okay, so this is another interesting plot. So we have these clustering that we are doing. How does the denoising PSNR look as a function of the number of clusters that you're learning? So this is a plot for the PSNR for Barbara at sigma noise level of 10 and noise level of 20. And you can see that, for example, at 20, the PSNR kind of increases until a certain point, until a certain number of clusters, max number of clusters, and then it kind of starts decreasing. Because at some point, the overfitting to the noise that comes into the picture, so just learning more clusters does not necessarily lead to better denoising. But until a certain point, you kind of learn richer and richer models, and that helps, particularly for images like Barbara, where you have a lot of different textures. Okay, what's the time?
57?
4:57, okay.
Yeah, I think we better.
What I will do is, I will take like 3 minutes to very quickly give the summary of the rest of the talk.
Okay.
Because I want you guys to have some message from the rest of the talk. So we have applied transform learning to compress sensing, and so essentially using transform learning as a regularizer in your compress sensing. Compress sensing is basically the problem of solving a system of underdetermined linear equations, but with a sparse deregularizer. Okay, and compress sensing is useful in a lot of imaging applications like MRI and CT, where you work with undersampled data. Okay, and you can use transform learning. You can use transform learning as a regularizer in compress sensing, and you have what is known as blind compress sensing, because you're blind to the model, and then we kind of.
Where are you putting a 2 non on X?
Oh, that's just in some cases where, for example, you're working with images which are 0 to 255, having an energy constraint seems to help. So. Okay, so, and then we propose kind of an alternating or block coordinate descent kind of algorithm for solving this kind of a blind compress sensing problem, and we derived, again, some global convergence guarantees, and we applied it to MRI. For example, here, you're undersampling the Fourier space or K-space of this image, and you want to reconstruct the image from the undersampled data. So if you do a transform learning based compress sensing, you get a result that looks like this, which is much better than just an inverse Fourier transform of the undersampled data. And you learn interesting transforms actually for the patches of these images. These are complex value transforms. This is the real part, the imaginary part. So it's quite interesting. And the main take-home message is that compared to other methods like the dictionary learning methods, the transform learning method gives you much faster reconstructions. It's about 10 times faster. It also gives better reconstructions. So
This is still an unsupervised technique. Is this still an unsupervised technique?
This is not optimized. This is just learning a square transform. Sorry.
This is just learning a square transform.
Yes.
But it's unsupervised.
Unsupervised.
You're not given a training set of reference
Mhm.
pairs.
You're learning. You're actually just given a bunch of undersampled measurements,
Mhm.
and you're using that to kind of learn your transform and also reconstruct the image from those measurements. So it's a kind of quite hard problem. But using a transform model gives you some very good results, and it has some good properties. So. And finally, we have something called online learning. So instead of collecting all your data in one place and then learning a transform for all the data, you can kind of learn the transform on the go as the data comes in. For example, here, the data YT are kind of coming in, streaming in to your system, and then you want to learn a transform. You don't want to store all the data. You just want to learn as and when a new sample comes in, and you want to do something with the sample. You want to denoise it, or you want to compress it. And so these are those outputs. So you can do this, and we have some kind of method or formulation that solves that for sequentially learns a transform over data that arrive sequentially. And this is very useful if you want to do like video denoising or just online denoising, just denoising streaming data, or you want to do classification real time. And for those kind of, or even if you have a very large image and you want to denoise it or do something with it, you don't want to have to extract 2 billion patches from the image. You want to be able to denoise it kind of in a sequential way where you kind of take a few patches, look at a few patches at once, and then go along and keep updating the transform and denoise or do something else with the image. And online learning is something that helps a lot in this kind of a scenario. And again, I have no time to talk about the details, but for example, if you look at these very large images, for example, this one has about 11 megapixels, and you try to add noise to these images and denoise them, then using online transform learning, you get some results like this. These are the denoising PSNRs at different sigmas for the images that I just showed on the previous page. So using transform learning gives you much better denoising results than, for example, using a DCT and denoising these images. And it's about as fast as the DCT in many scenarios, in many of these examples. So you don't lose much in runtime, even though you're learning, because the main computation comes from applying applying matrices on vectors. In transform learning, that's kind of the main computation, because there's no NP hard sparse coding, none of that. So that's kind of, DCT does it a little bit more efficiently. It has the n log n complexity because you can apply a DCT on a vector more efficiently. But because here we are not learning the kind of a transform that's a Kronecker product, we cannot apply it more efficiently than just an n-square complexity, with an n-square complexity. And you can finally, you can apply such an online scheme for video denoising. So you have kind of frames, the video frames coming in, and you want to denoise these frames. So what we do is we collect a small set of frames at each time instant, sort of M frames. So you have the latest frame, which is ZT, and you have up to some M-1 past frames. And at each time t, you denoise these collection of frames using kind of, you learn a 3D transform for the 3D, because it's a collection of frames, you can learn transforms for the 3D patches of these collection of sets of frames. And you can learn this in a kind of online manner. You don't have to just take all the 3D patches out and learn a transform for that. You can just go along these 3D patches. You can kind of draw a curve as the frames come along, and you can kind of learn a transform and denoise these patches. And once you denoise the 3D patches, you just put them back in their locations in the frames, and you average them together to get the denoised frames. So that's how you denoise. And what we found is that if you do this kind of a transform learning kind of approach for video denoising, you get much better results than some of the state-of-the-art methods. For example, this I just put before the talk, so it's not in a very nice-looking state. So the rows here, these are some different videos: Salesman, Miss America, Coast Guard, and different noise levels. Number is for just a DCT-based denoising, 3D DCT for the 3D patches. And this is using some form of KSVD, a dictionary learning algorithm. And these are for the BM3D, the variants of BM3D for videos, which is VBM3D and VBM4D. And then these are the results for transform-based denoising of the videos. And we use kind of different patch sizes. So this is for a smaller patch size and a larger patch size. And you can see that for a lot of different videos, you get some significantly better performance. For example, see here, 31.72 for the VBM 3D approaches, and about 33 for transform learning. So you get significantly better denoising by learning these transforms in an online way, and you can do it very efficiently because, and without much memory requirements and so on, because you don't need to store all the patches and so on. You just need to store a few patches for a few frames at each time. And this is just a frame from one of the videos, the noisy frame, and this is what this is the reconstruction that we got with our scheme. Certainly looks much better than this because you cannot really make out some of the features here by just looking at the noisy image, whereas by learning this transform model, you can find some of these features very nicely. And this is just the error map for WidowSat, and for this is our method, WidowSat. And this is the VBM 40, which is the variant of BM 3D for video denoising. So you get some much better errors. There is some error here, apparently because there is some motion going on of the hands. So the error is mainly concentrated in tracking this motion by the 3D transform. Okay, so, and I didn't talk much about how we are solving these, solving the online transform learning problem and so on, but we kind of use, again, alternating minimization techniques, and there are some very nice asymptotic convergence properties for this online sparse transform learning. And so I showed some examples for image denoising, video denoising, and some acknowledgements, my advisor, some collaborators and colleagues, and NSF. Thank you.
Anybody want to ask any questions before we?
Yeah, maybe I have a first question. The key to your algorithm is the recognizer, right? It is the norm of the transformed matrix minus the log of the determinant of the transformed matrix. How did you find such a recognizer? And
not just the
there are any similar recognizer?
It's the model itself. So this term over here, this wy minus x, this is kind of linear in the transform w and x. Whereas if you look at dictionary learning, the alternative model, you have something like y minus d times x, where d and x are both unknown. So you have a kind of bilinear problem. So it's a more complex problem, and this is a much simpler problem. So we kind of take advantage of that and get faster solutions and better guarantees.
Yeah, but if you change the form of the recognizer, maybe your algorithm.
We have tried a lot of different recognizers for it. I couldn't talk about all of them. So we have tried what's known as doubly sparse transform learning, where we constrain the transform to be sparse. So it's a product of a sparse matrix and a fixed transform because it allows for efficiency in applying.
So you can apply different forms of recognizer?
You can apply very different forms of recognizers, yes.
Okay.
It all depends on what kind of properties or what application you're looking at. Because, for example, the octopus allows you to kind of cluster the data. It's useful for classification. And so depending on, and doubly sparse, it allows for efficiency in storage and all these things. So depending on what properties you want, you can enforce a certain kind of regularizer. But not all regularizers, all kinds of regularizers are going to work. So.
Okay.
So, so you mentioned something about DCT is faster because the chronicle production.
Yes.
At least
Because because applying the DCT, you just need n log n.
that's one thing, and then you can apply it to the version and the column.
Yes.
So at least the second part, could you look for a
Separable transform.
W that, yeah, separate.
Yeah, we have been looking at separable transforms, but adaptive separable transforms don't seem to work as well, really, because when you impose separability, so instead of learning an n by n transform, you're learning a square root n by square root n transform, and you're applying it on the two sides of the patch. So
You can do the diagonal.
no, the thing is, the square root n by square root n transform has n free parameters.
That's it.
And the signal itself has n, well,
transform.
The transform itself is the overall transform in the unstructured transform case has n square free parameters. So the ratio of the free parameters goes as 1 over n. So as the problem size increases, the separable transform becomes more and more and more constraining. So that's kind of limits you asymptotically in terms of performance, because you don't learn much with the separable transform as you do with an unstructured one.
Is that the main thing, or is it also that you won't learn some of the, so you learn either column structures or row structures, I mean, you want to learn more, in textures, you won't learn arbitrary.
Yes. Yeah.
I thought that might be the main.
That's kind of the same thing.
Yeah, that's the same thing, because it's
Well,
related to the
fine,
structure.
it's related to the number of free columns.
Okay, so if you have more questions or want to talk about other flavors of transform learning and so on, you can